Okay, today we're looking at Newton's method. Newton's method is a way to estimate a root of a complex function that is difficult, or if we don't even have a way to calculate that root. So we use the idea of a linear approximation to find points closer and closer to the root, and then using the tangent line to find the roots. So let's start. This is actually just going to be a general example. I'm going to start with just a general function of x. So I'll just call this graph f of x. I'll call it in blue since my line's in blue. And then I'm going to just guess a point. So just any point. So, or maybe I'm not just guessing. Maybe I have a point that's easy to calculate and I want to start there. So say I guess at x1. Then I can find the f of x function. I can plug in x1 because I'm given f of x. So this is a given value. And x1 I pick. Or maybe I've been told what to use for x1. Or maybe looking at the graph, it helps me decide what to choose for x1. Either way, I know what x1 is, I know what f of x is, so I can plug x1 into f of x, and I can get a value for f of x, which would be the height of this red dotted line. That would be the y value at this point. I also know how to find the derivative. So I can find this because I have f of x, and I can find the derivative and evaluate it at x1 to find the tangent line. So the tangent line here will have the slope of the derivative. Looks like there's my tangent line-ish. And you can see the tangent line, once it goes to the x-axis, it is closer to the root than the first guess was. So that gives me an x2 value. My x2 is a closer approximation to the root, but it's not quite at the root yet. So I can do it again. And I'll start at x2. I'll plug in x2 into f of x. I'll get this value for the f of x now. I can find the derivative of the f of x, and I can find a tangent line, and that tangent line gives me an even better estimate. So now I found x3. It's pretty close, but maybe I want to get even closer, so I can do this as many times as I want until my number converges to the root. So now I'll take my f of x3, which is very short. That would be f of x3, this little height, and take the tangent line at that point, and you can see now it's getting closer and closer to the root. So my x4 might even be the root. So using that linear approximation over and over again, linear approximation, you might remember, tells us that we can estimate a function value that's close to a number that we choose and that tangent line. So if I wanted to find a number that was close to x1, I could find it with linear approximation. So moving that line closer and closer to the root makes that linear approximation even more accurate. All right, so this is the idea of Newton's method. And I know how to get f of x. I know how to get the derivative at f of x. This is f of x1. And I know how to get the derivative of f of x and then evaluate that at x1. So I know how to find that. But what I wonder is, how do I get x2? How do I get the next value? So once I have x1, how do I get x2? Once I have x2, how do I get x3? So let's look at just x1 and x2 first. First, we know what x1 is. We have that. We picked that number. We know f of x. We know the derivative of f of x. But how do we find x2? Well, if I call this, I kind of highlight a triangle here. So this triangle, the base of that triangle is the distance between x1 to x2. So let's call this base of that triangle delta x. Then I could say delta x, well, I could say x2 is equal to x1 minus the change from x1. So delta, I'll call it x1, delta x1. So if I can find out what that delta x1 is, then I can find x2. Okay, so what is it? So I'm looking at that triangle again, and I think, oh, this is really the slope of this tangent line. So the tangent line is rise over run, the slope is rise over run, and to get to this point on that tangent line, it's rise over run. And I have both those values. So I can get the slope of the tangent line is equal to the rise over the run. Okay, but I also know that slope is not just equal to that physical rise over run that I can see in that triangle, but it's also equal to the value of the derivative at that point. So the slope of that line evaluated at that point is the derivative evaluated at x1. So do two different ways to write the slope. I can use this equation to solve for delta x. So if I solve for delta x, I'll multiply both sides by delta x. And then divide both sides by the derivative. And now f of x1 and f prime of x1 are both numbers. So I can find delta x, and I will use that to substitute back into this, and now I can find x2. So x2 equals x1 minus, and then our delta x1 is substituted with this function divided by the derivative function evaluation. So we could do f of x1 over the derivative evaluated at x1. Remember x1, f of x1, and the derivative evaluated at x1, those are all just numbers. So now I can calculate x2. And then I can do the same process. So now I have a number for x2, so I can do that same process to find x3. So x3 will equal x2 minus the function evaluated at x2 divided by the derivative evaluated at x2. And I can repeat that process to get our x4. Taking the previous value, evaluating the function at it, and evaluating the derivative at that point. So I can generalize this. I can do this as many times as I want. And while I can kind of generalize it, so I can say I can get the, if I have 1xn, so I can find the next one by subtracting the function at that value divided by the derivative at that value. So that will give me my next x. So that function, I just calculate it over and over again until I get my numbers convert to one number, and that will be my root. And that is Newton's method. Whoops. So with Newton's method, we're trying to find approximations of the root, and we get this formula. That we just demonstrated. And we can visualize it here on this website. And you can pick a point on this website, you can kind of play with it. Like if I'm trying to get to this root right here, then maybe I pick that point and I plug in a number there, and you can see that using that derivative tangent line, I can get a little bit closer, and then I do it again and I get closer every time. And on this table you can see the y values are going to 0 and the x values are converging. So we can see the root, whoops, is at that 1.801938, or that's an estimate of the root to 3 decimal places. All right. So there's a picture of what we just described in that process and how we get that function. Now, this works if the numbers that we're getting are getting closer to the root. Then we can see that convergence. We can see those numbers getting more and more, and eventually we'll see them giving me the same value every time because I'm as close as I can get. So you can see the numbers getting, the delta x gets really, really, really small. And so we'll see what that looks like. When it doesn't converge, then our numbers kind of bounce all over the place, or I might even get to a point where I need to divide where my derivative is 0. For example, if I were to take this function, if I happen to pick this point, and then I would get the tangent line equal to 0, well, that's not going to give me anything at all. So the closer I am to that flat derivative where the slope is 0, the less likely I'm going to be able to get my root. And when that happens, I just pick a different x. So if it doesn't converge, then try a different x to start. And the graph can often help with that. When you see the graph, the steeper the line, the more likely you'll get a root, and also the closer you are to the root, the more likely you'll get to a root. Okay.